Here we go. Good morning, everyone. Welcome to Life Seminar Series. Before I hand over our speaker today, just other seminars are available for you to watch via the intranet webpage. If you just go to the Life Sciences departmental page. And then also, next week we have another seminar coming up from Simon Loader, who's going to talk about his recently published guide of Tanzanian amphibians. There'll be a Q&A that'll be live during the talk, so please feel free to pop questions in for our speaker. And with that, I'm very delighted to introduce our speaker today. Today we're joined by Galina Jönsson, who's currently a PhD candidate based at the NHM. Galina earned her BSc in ecology from University of Edinburgh, and then an MRes in Biodiversity, Conservation and Diversity from University College London. In addition to collaborators at Centre for Ecology and Hydrology and Imperial College London, she's working with our own Andy Purvis and Ian Kitching on her project. And in addition to butterflies, she's also worked with several other insect groups, including a very interesting recently published paper in Insect Conservation and Diversity on using museum specimens to predict spatio-temporal patterns through time. I'm sure she's going to tell you lots more about that today. So with that, I'm delighted to hand over to our speaker today. Thanks very much.
Thank you very much, Jeff. Right, so I'm not sure who's attending as I can't see you, but I'm Galina, doing my PhD at NHM, and I'll be talking about how we can use butterfly specimens, and as Jeff said, with a sprinkle of social wasps to extend current biodiversity time series. But first, I'd like to mention that I have by no means done the things I'll be talking about by myself. Everything's been done with the help of my brilliant supervisors and the help of many others. Right, so let's get cracking. I'm sure many of you are familiar with shifting baseline syndrome, which is basically where ecological expectations decrease with each generation. So the baseline state of biodiversity becomes that experience within each generation. And as actual biodiversity levels are decreasing over time, that we know, we get a kind of generational amnesia resulting in, frankly, wrong and inappropriately low baselines. So I often see the windshield phenomenon as being used as some kind of proof for shifting baselines. And that's the claim that fewer insects accumulate on windshields today compared to some decades ago. But as I was barely born back then and certainly did not drive, I would like some more robust evidence. So here are a few headlines which show that even in countries with some of the best biodiversity data, one of those countries being the UK, our current baseline for many taxa is the 1970s. And this is because almost all species monitoring schemes started in the 70s or later, where a species monitoring schemes produces so-called standardized data, basically where people go to the same place, same time of year, multiple years in a row, record species in the same way. Statistically more easy, or like less difficult, I should say, data to analyze. So in other words, the 70s is our baseline because of historical data deficiency. But I would argue that the 70s is probably a rather poor baseline. So fair enough, it captures the start of this kind of clear directional warming we started seeing in the 80s, as evident from the graph here showing average global temperature anomaly over time. But we also know that, at least in the UK, most large-scale landscape transformations happened in earlier decades. So, for instance, we know that industrialization, urbanization were associated with large-scale land use changes. Coming up to the 50s, we have huge agricultural intensification, increased pesticide use, further conversion of natural habitat into mostly agricultural land. And I reckon that these factors must have affected wildlife population, right? But without species trends prior to the 70s, it's difficult to estimate the separate effects of these anthropogenic pressures, which would really, having that kind of data would really help us predict the outcomes of different conservation efforts that we make today, given accelerating climate change, biodiversity loss, etc. But we do have tons of specimen data dating prior to the 70s. So through digitisation projects like synthesis, collections are becoming increasingly available for research. So specimens have been used to document long-term changes in phenology, trait evolution, etc. But unfortunately, we haven't really made much progress in using them for tracking abundance or distribution changes. And this is because the downside of specimen data, or perhaps I should say the metadata, so the where and when the specimens were collected. The downside is that they are so-called opportunistic. So in contrast to the standardized data that we get from monitoring schemes, we don't really know what the sampling strategy of specimens were, the why and how specific specimens were collected. But what we do know is that collectors had different kind of goals with their collecting. So some wanted one of every species, others wanted every variety of a single species. And this introduces a number of biases and inconsistencies in the data. So those that have used collections for long-term trends have often received a fair bit of criticism. One example is Boylan colleagues, who I'm sure are great scientists, but they estimated abundance from specimens for the monarch butterfly and its milkweed host plant throughout the 20th century. And they corrected for this inconsistent specimen sampling effort by basically dividing the number of, and this was in the US, so dividing the number of US monarch specimens by the total number of US Lepidoptera specimens. Yeah, and as you can see, received some criticism. One with the quite discouraging title, "Tracking Trends in Monarch Abundance Over the 20th Century is Currently Impossible Using Museum Records." They said that the correction for variation in sampling effort was inappropriate. And another critic agreed that the correction method was inappropriate. And they also reanalyzed the data and found different trends when they, so remember that Boyle used the number of monarchs divided by the total number of Lepidoptera. So when Webridge reanalyzed the data, but for example excluded moths from the grand total Lepidoptera specimen number, they got completely different results. But I still think that collections definitely have a role to play in producing long-term trends, but we clearly need better ways of accounting for unknown, that's the word, and biased sampling. So naturally, for my master's project, my supervisors and I felt that we had to join in on this somewhat controversial topic. And 2.5 years later, our paper on dealing with biased specimen sampling came out, and this was a couple of weeks ago. So we looked at 3 social wasp species in England only since the year 1900. We used NHM collections and survey data from a recording scheme, the Bees, Wasps and Ants Recording Society, BWARS for short. And our solution was to use an occupancy model, and these separately model sampling effort biases and use those results to inform the occupancy estimates. And by the way, the occupancy is the proportion of an area where a species is found, but that will become more clear later on. But as mentioned, as we had data from different sources with different sampling biases, we extended the model to separately estimate the bias in the survey data from the bias in the specimen data as two kind of independent realizations of the same underlying state, the occupancy, and would then let both estimates of bias be used to inform the occupancy. And I won't go into further detail about any of the specifics regarding the statistics beyond this, but I'm very happy to chat about it afterwards. Post your question in the chat box or send me an email if you really want to get into the nitty-gritty. We found that 2 species hadn't changed much since the year 1900, whilst the European hornet on the right here had. And as you can see on the x-axis here, which is occupancy, no, the y-axis that is, sorry. So if the occupancy is 1, the species is found in all of England in this case, and if it's 0, it's not at all found in England. So these were the first kind of quantitative trends for species prior to the 70s, for these species prior to the 70s, which demonstrates that specimen data can be used to produce long-term trends. But as I said, we only looked at 3 species with relatively few specimens. And sorry, to answer those like really important ecological questions in terms of effects of anthropogenic pressures, etc., we need to scale up these preliminary analysis kind of to more species. And if we were to use more species, we would probably find that our model formulation is a little bit underdeveloped and maybe a little bit too simple. So yeah, in short, we need more data to understand and develop these kind of models. And that's where the Great British Butterflies come in, or in my case, form the basis of my PhD project. So butterflies are probably the insect group whose ecology we know the most about, and they're also good indicators of greater habitat and climate change, since their caterpillars only feed on one or a few host plants, and they're also sensitive to changes in temperature and climate, etc. Additionally, we know that 5 species have already gone extinct in Great Britain since the 1800s. So additionally, we have a lot of specimens as well as contemporary observational records, at least compared to most other insects. And these data, frankly, have quite amazing spatiotemporal coverage. So we of course have the iCollections dataset, the project where NHM digitized around 500,000 British Lepidoptera specimens in the collection. And then we also have literally tens of millions of contemporary observational records with the first standardized scheme, the UK Butterfly Monitoring Scheme, UK BMS for short, starting in 1976. So for UK butterflies at least, 76 is our current baseline. There's also loads of other modern initiatives which produce everything from super standardized data to very opportunistic data, and I'll show you an example of the more opportunistic modern data on the next slide. But to summarize, there's a lot more variation among and between the sampling effort of specimen collectors as well as modern day recorders compared to the WASPs I showed you earlier. Right, so to account for these differences, I compared individual people's sampling biases, and I'll show you how people from 3 different data sources compared. Firstly, individual NHM collectors. Secondly, the people who do these standardized UK BMS transects. So they walk along a transect, a specified transect, and record every species they see. And then thirdly, people that use a smartphone application called iRecord, where they can submit any butterfly sighting at their leisure, really, without any specified sampling method. But I think that often they have to take a photo so that a species ID can be verified. And this graph here shows you that NHM collectors, the black line, tend to collect only one or a few species at a single location, whilst BMS recorders, the purple solid line, record multiple species, which makes sense as they're meant to record every species observed at their transect. And then the iRecord users, the pink dashed line, fall somewhere in between and varies quite a lot. Again, not too surprising as there's no protocol for how to record. Sorry, water break. So here we can see that both BMS recorders and iRecord users tend to record more common species, whilst NHM collectors focus on rare species. And there's also a lot more variation among the NHM collectors. So these were only 2 of 12 kind of biases that I looked at, and the 2 I showed you were taxonomic biases, but I also looked at spatial and temporal biases. And I used the results to formulate an occupancy model that explicitly accounts for these biases in sampling between and among the data sources. So I then used the model to produce occupancy trends across all of Great Britain for each of 53 resident butterfly species. And this plot shows the average annual occupancy since the year 1900, where 1900 is the 0. Again, average across the 53 species, and again across all Great Britain. And the vertical line here indicates the year 1976, the UK BMS, the standardized recording scheme, started. So by just looking at it, in my opinion, it doesn't look too bad. And the numbers agree. So on average, butterfly occupancy in Great Britain decreased by around 15% since 1900. And also, we don't see any like overwhelming evidence suggesting that we are suffering from shifting baseline syndrome, because then we would expect to see much more change prior to 1976 rather than after. However, we get a very different impression if we divide a species into whether they are habitat generalists or specialists. In fact, we get something resembling a giant squid. So the generalist, blue dotted top line, and these are also known as wider countryside species, they've done great and increased by almost 90% since 1900, whilst the specialist, green dashed bottom line, have not done well at all really and decreased by approximately 56%. So, although the uncertainty of the estimates is greater in the early years when they are based on mostly natural history collections, which again makes sense as there's a lot less of this kind of data, the estimates are still precise enough to show big difference when we divide habitat specialists from generalists. And when we do this kind of division, it's also clear that most occupancy change happened before our current estimate, or our current baseline rather, of 1976. It looks like most change happened between the 50s and the 70s, and this is interesting because it suggests that agricultural intensification of the 1950s could be a cause, or at the very least some kind of tipping point for the subsequent changes that we see. But I wonder, is it fair to divide species into either habitat generalist or specialist and assume that within each of these two groups, all species show the same long-term trends? It appears that no, it's not. So here are two examples of species that show opposite trends compared to their respective groups. Remember that if the occupancy is 1, they're found across, in this case, all of Great Britain, and if it's 0, they're not found in Great Britain. And these have different occupancy axes. So the silver-washed fritillary on the left is a habitat specialist that has increased in recent decades, whilst the wall on the right, a habitat generalist, has shown quite worrying declines, which have been suggested to be due to climate change. And my results here also support that, because the start of its decline coincides with that of sort of directional warming. But instead of dividing all species into two quite arbitrary groups, it might be more useful to look at whether their functional traits can be more informative in explaining these long-term trends, where functional traits are basically characteristics that define the ecological roles of a species and basically whether they will survive in a given environment. And I looked at species-specific values for 15 such traits. So these graphs show community-weighted means for 2 of the traits, mobility and wingspan, over time, where community-weighted means basically is the sum of all the species values for a specific trait, basically multiplied by their relative annual occupancies. So we can see that over time, the community, which in this case is the resident butterflies across all Great Britain, has moved towards smaller and more mobile species, as well as ones with many host plants and less feeding specializations, and species that lay many small eggs. So in other words, towards species with traditional generalist traits, right? But when we look at functional diversity metrics that summarize changes in the 6 traits I just showed you, in addition to another 9 traits that I looked at, again, across all of the species over time. So when we look at these kind of summarizing diversity metrics, it appears that things are not just as simple as specialist versus generalists. We actually find that functional divergence has increased whilst functional evenness has decreased, indicating that there's kind of a lot more complexity under the hood of this dichotomy to be explored. And yeah, this is what I'm currently working on. I'm really trying to wrap my head around. The schematic here shows one possible explanation for the results by considering 2 random traits, antennae length and colorfulness. So I have 2 hypothetical communities, and each butterfly represents 1 species in each of the communities, with their size indicating the occupancy of that species. So the bigger the butterfly, the higher the occupancy of the species. So if we start with the hypothetical community, like the one on the left, where all 9 species have equal occupancies, functional evenness decreases when species occupancies become less evenly distributed among possible trait values, as seen in the second hypothetical community to the right here. And similarly, functional divergence has increased in the second community to the right, as species with high occupancies are more functionally dissimilar. So high occupancies here are colorful and long antennae, as well as non-colorful and short antennae. But remember that I'm looking at 15 traits as opposed to 2, which makes the, at least for me, the inferences a bit more tricky, because yeah, it would basically be like 15-dimensional space as opposed to 2. But the results suggest that there might be specific combinations of specific generalist traits that have been especially advantageous throughout the 20th century's anthropogenic pressures, and therefore increased in occupancy relative to other species. So yeah, as mentioned, and this is what I'm currently working on, and I'll definitely be the first to admit that there's a lot I've got to explore and figure out here. And that leads to my conclusions. So firstly, natural history collection specimens can definitely be very useful to produce long-term trends. Secondly, yes, we have a lot of uncertainty early in these long-term time series, basically the main body of the squid, and then a huge degree of precision later on. But the magnitude of change we see between historic and later periods is way greater than the uncertainty, so that means that we can make inferences. Good. Thirdly, at least for butterflies and wasps in the UK, most change happened before the 70s, indicating that it is a poor baseline and that we appear to be suffering from shifting baseline syndrome. And finally, so although generalists versus specialists can give useful indications of long-term trends, the reality is far more complicated. Yeah, every species has its own particular quirks, and there will always be exceptions, but we have to generalize in one way or another and can't capture all variation. But I propose an approach that uses multiple ecologically important functional traits rather than this kind of habitat use dichotomy. Right. Thank you very much for your attention. I'm gonna stop sharing my screen now, and I'm happy to answer any questions. Thank you. How do I do this?
Great, thanks very much. That was an excellent talk. So the Q&A is open. If anybody would like to ask Galina a question. Oh, we've got some coming in. While we're getting ready to publish those, I'll start it off. I had a question about the functional traits, which was, are you using single values for, say, like morphological variables per each species, or is there any thought that's been put into capturing intraspecific variation in those approaches?
No, I have not captured interspecific variations. I've tried to make sure to use trends that are not describing occupancy or species interactions with their like current vegetation, because those associations might change over time, nor like correlated traits or traits with high plasticity, and instead traits that kind of govern resource use rather than describe current resource use, if that makes sense.
Mm-hmm. Thanks. So Gavin asks, is it straightforward to model climatic requirements of species functional traits?
So can you repeat the question, please? Is it straightforward to model climatic what?
Requirements as species functional traits. Yeah. Not sure if it's possible for Gavin to provide a little bit.
I haven't really. Well, I've used one of the traits I used was like adult thermal hardiness score, but yeah, straightforward. Not really. As I said, I'll be the first to admit that these kind of like functional trait analyses are quite new to me, and I tried to include a few traits on phenology and like thermal tolerances, but yeah.
Gavin's also said, great talk, good to have the wasps and the wasp food. And then Vincent Smith has asked, what is the correlation between specialist-generalists versus frequency in collections and observations? I realize you are trying to control for this, but in my experience, specialists are rarer and harder to find, but there are a lot more species diversity. Thus, more likely that some species will disappear or drastically reduce in population. Whereas generalists are more common, but there's a lot less species diversity.
Right, so I haven't looked at that correlation specifically, but I would assume that, as I showed on one slide, that in the gem collections, that rare species are kind of overrepresented in the collections, and that rare species would be more likely to be specialist species. Like, I haven't looked at that specifically.
Cool. Jeff Martin has said there are 59 species of butterfly in the UK. So who are the missing 6 and why weren't they included?
So some of them are because they have a lot of vagrants from the continent, which makes it quite difficult to model whether they whether that's the actual UK or Great Britain occupancy, or whether they're just vagrants coming over the channel. That's why. So I haven't quite figured out how I would do that. So therefore, I focus on the ones that I know are on the island in this neighborhood. Jeff.
Any other questions? We've got plenty of time for discussion if we'd like. Yeah. So while
they're not doing very well.
Yeah. One more quick question I had was, and I understand that you'd probably be looking exclusively at natural history collections for these data, but has much been done pre-1900s? So I'm thinking about shifting into the Anthropocene and everything about the baselines and things.
So originally I wanted to extend it back to at least 1850, but unfortunately there's not enough specimens with where the collection date and collection location is precise enough to use in the kind of analysis I use.
Cool.
I would love to do it. If we find more old butterfly specimens, it's definitely possible, but we just need more data.
Cool. Yeah, that seems like that'd be with more connected museum networks across the world. That might be really open up some of those opportunities. It's exciting.
Definitely. Yeah.
John Rose has a great question. When there is mention of numbers of insects impacting on the front of road vehicles, is there any mention of changes in vehicle design over decades, changes in aerodynamics, etc.? So an engineering question.
I'm afraid that's not my field of expertise. And there has actually been like a few studies that I think kind of prove that that's a thing, but it's just the kind of, I see it as anecdotal evidence that I often hear, but I have no idea about the sign of cars. I don't have a driver's license.
And so Mike Sadka says, not a question, but really nice to see the iCollections dataset getting used. So,
it's a brilliant dataset, and I say it's underused, but yeah.
Great. Any other questions before we sign off for the day? All right. Well, I'm as Galina said, you can send her emails if you have additional questions, and this talk will be available on the Life Sciences webpage if you wanted to go back and check anything. But I want to thank our speaker again for a fantastic talk. I can't wait to see, well, there's already really interesting results, and I'm really excited to see where you go next with it. So thanks very much, and I hope everyone has a great rest of their week.
Thank you.